This notebook covers ensemble learning, bagging, and random forest boosting algorithms, including AdaBoost, gradient boosting, XGBoost, and LightGBM, as mentioned, and voting classifiers. Imports. Here are imported standard libraries such as NumPy, Pandas, Matplotlib, Seaborn for visualization. Next, we implemented random forest under the bagging family. Code, generated data, random forest training, and future importance. First, I started I started with a synthetic classification data with by taking 1000 samples, 20 futures and 15 informative. To control complexity, then I split to train and test. I initiated random forest classifier with 100 estimators, max step 10 and fit it. Later, I print accuracy on the train set, a 5-fold cross-validation score on the training portion to show generalization. Finally, I compute a plot future importance. I took top 10 and plotted it. Random forest uses bootstrapped aggregation and random feature selection per split to reduce variance. Hyperparameters like n estimators and max step grade compute versus overfitting. AdaBoost. Now we shift to boosting. AdaBoost is an early boosting algorithm that focuses on misclassified examples. Code. I instantiate AdaBoost classifier. N estimators are 50, learning rate is 1, and fit to some train test split. Then later I fit the model. I report test accuracy and a 5-fold cross value mean. AdaBoost sequentially trains weak learners, often decision stumps. We reweighting samples. It's more about bias reduction and can be sensitive to noisy data and outliers. Gradient boosting. Gradient boosting builds trees sequentially by fitting residuals. Code. I use gradient boosting classifier, 100 estimators, learning rate 0.1, max step 3, 3, and fit and predicted. Later, I printed accuracy and cross validation. Learning key things which we have to observe in gradient boosting. Learning rate, number of estimators, and tree depths are crucial. Lower learning rates with more trees often yield better performance. Early stopping or subsampling can reduce overfitting. XGBoost. XGBoost is a performant regularized gradient boosting. Code. Here I initialized XGBoost classifier with the evaluation metric of log loss. I reported accuracy and cross validation scores. XGBoost adds regularization, optimized tree construction, missing value handling, and parallelism, which often gives both speed and accuracy gains. Voting classifier with LR, RF, and SVC. Code. Voting classifier is a combination of heterogeneous models. Here I combined logistic regression, random forest classifier, and support vector classifier with probability as true. Key things which we have to observe. Hard voting uses majority class labels and is fast. Soft voting averages class probabilities and usually performs better if base models output calibrated probabilities. Model diversity is important for gains. Now we gather predictions and compare the performance of all methods side by side. By assembling all predictions and the resulted predictions are plotted and viewed in data frames by using pandas. Here I have collected predicted label arrays for random forest, AdaBoost, gradient boosting, voting classifiers, and optionally XGBoost. Builds then builds a data frame of model names versus accuracy computed against y-test. It prints the summary table and visualizes the accuracies in a bar chart. Emphasis. This is a quick reproducible way to compare methods on the same holdout set. Clarify that proper model selection should compare cross-validated metrics or used nested CV for hyperparameter tuning. Bagging versus boosting. Sequentially, to correct prior errors and reduce bias, we use boosting. Sequentially, parallelly on bootset, bootstrapped subsets and reduce variance, we use bagging. Random forest prevents overfitting. How? Let's understand. Random forest prevents overfitting with bootstrapped sampling via max depth and mini samples parameters. Why XGBoost often outperforms gradient boosting. XGBoost adds L1 and L2 regularization, which are lasso and lasso regularization. Like those are loss metrics, loss evaluation metrics, efficient parallelized algorithms, due to which XGBoost outperforms gradient boosting. So when to pick hard and soft voting. Hard voting picks the majority levels. Soft voting averages predicted probabilities and usually performs better if individual models return reliable probabilities.